Hello friends, I welcome you in lecture number 19 on partial derivatives. In this lecture, we are going to talk about local extreme values for functions of more than one variables. Local extreme values means either local maximum values or local minimum values. You are already familiar with this concept for functions of one variables in your 12th standard. So first we recall what is the meaning of local extreme values for functions of one variable, say fx. So as we know, suppose I consider a graph of this function. Suppose I am having this type of graph for this function fx. Suppose this is x-axis, this is y-axis. Then from the graph we can easily say that this is the local maximum value, this is local minimum value, similarly this is local maximum value, this is local minimum value. So local maximum means maximum value of function in some interval. For example, if I consider this point, suppose this point is x equal to a, then I can say that if I consider a value of function at this point, then it is f of a, and we can see that this f of a is greater than or equal to fx for all x which are in the neighborhood of this fixed point a. We can simply write that for all x near a. For example, if I consider this interval, suppose this point is c and this point is d, then I can say that value of function at x equal to a is greater than or equal to fx for all x in this interval, for all x belongs to open interval c to d. We can see if we take any point x here in this interval, either here or here, then fx is always smaller than f of a. So we can say that this f of a is local maximum value of fx in this interval, open interval c to d. So this is the meaning of local maximum. The function f of x is said to have local maximum at some point a if f of a is greater than or equal to fx for all x in some open interval containing that point. For example, if we consider this point, suppose this point is say b, then this f of b is local maximum value of fx. We can consider this interval. If I consider this interval from e to f, then we can say that value of function at x equal to b is greater than or equal to fx for every x in this interval c to d. Similarly, we can talk about local minimum value. For example, if we consider this point, then this point is local minimum. Suppose this point is denoted by p, then if we consider some interval containing p, for example, if we consider this interval which contains p, then we can say that value of function at x equal to p is smaller than fx for every x in the interval containing p. Suppose this interval is rs, then we can write that for every x in the interval rs, f of p is smaller than fx. So this f of p is local minimum value. So this is the meaning of local maximum and local minimum which we study in our school level. Now we are going to generalize this concept for functions of two variables as well as for functions of three variables. So as we discussed, suppose I consider some fixed point a, then if I obtain that f of a is greater than or equal to fx for all x near a, or for all x in an interval containing a, then f of a is said to be local maximum value of fx, or we can say that fx has local maximum at x equal to a. Now we can generalize this to functions of two variables. Suppose I have function of two variables, say fxy, and suppose I consider a point AB in the domain of this function. Then if this happens, that value of function at point AB is greater than or equal to fxy for all points xy near this fixed point AB, then we can say that f of AB is local maximum value of fxy. Same thing for local minimum value. For local minimum, we have f of a is less than or equal to fx for all x near a. For all x near a. If this happens, then we say that f of a is local minimum. So here also, instead of function of one variable, we have function of two variables. If f of AB is smaller than fxy for all points xy near AB, then we can say that f of AB is local minimum value of fxy, and either local minimum or local maximum, they are known as local extreme values. Local extreme value means either it is local maximum or local minimum. So this is the generalization of local extreme values from functions of one variable fx to functions of two variables f of xy. Similarly, we can have this generalization for functions of three variables also. Suppose we have function of three variables, say x, y, z, and suppose we have this point ABC in the domain of this function, then f of ABC is local maximum value if value of function at point ABC is bigger than f of xyz for all points xyz in the neighborhood of this point, for all xyz near this fixed point ABC, and f of ABC is local minimum if we have less than or equal to sign here. So this is the meaning of local extreme values for functions of more than one variables. Now the question is, it is not easy to decide from the definition. Every time from the definition we cannot decide that which point at which point function will have local maximum or local minimum. So for that we have certain tests which we are having in 12th standard also. Okay, so we are going to generalize those tests. We know that if we have function of one variable, then if this function is differentiable, then this function will have local maximum or local minimum at those points at which its first derivative is 0. F dash x equal to 0. Solution of this equation will give us the points at which function is either local maximum or local minimum, and same result we have for functions of two variables and three variables also. We are writing for functions of two variables. So as in this case here we find out the points at which function will have either maximum or minimum by solving this equation f dash x equal to 0. Now for functions of two variables we are having two first order partial derivatives, del f by del x and del f by del y. So the points at which both the first order partial derivatives are 0 will be the candidates for local maximum and local minimum. So same result we are generalizing here. Here function is local maximum at those points at which f dash x equal to 0, and here function have local maximum or local minimum at those points at which both first order partial derivatives are 0. Another thing is we can have non-differentiable function also. So the point at which f dash x does not exist, those points are also candidates for local extreme values. So same thing here, the points at which fx and fy do not exist, either fx or fy or both the derivatives do not exist, are the points which are also candidates for local maximum or local minimum. So from this we can say that the candidates for local maximum or local minimum are those points at which either fx or fy or both the partial derivatives do not exist, or if function is differentiable, then the points at which both the partial derivatives are 0 are the points which are candidates for local maximum or local minimum values. So this is known as first derivative test. So that I have written here, first derivative test for local extreme values. If fxy has a local maximum or minimum value at an interior point AB of its domain, and if the first partial order derivatives exist at that point AB, then they are always 0. So the point at which function is either maximum or minimum, at that point both the first order partial derivatives are always 0 if they exist. And we can write down the definition for critical point. Critical points are those points at which these partial derivatives are 0 or they do not exist. An interior point of the domain of a function fxy where both fx and fy are 0 or where one or both of fx and fy do not exist is known as critical point of f. In other words, if we have this point AB, then this point is a critical point if fx or fy or both do not exist. If both the partial derivatives or at least one partial derivative does not exist, or if they exist, then both the partial derivatives are 0 at this point. So this type of point is known as critical point. So sometimes they ask the definition of critical point also. The only points where a function fxy can assume extreme values are critical points and boundary points. So whenever you are having a problem of finding extreme values of a function fxy, then the candidates for extreme values are critical points and boundary points only. Now, as in the case of first order, as in the case of functions of one variable, we are having second derivative test for functions of two variables also. If you recall that second derivative test for functions of one variable is, first we find out the critical points by solving this equation f dash x equal to 0. Suppose x equal to a is critical point of fx, then x equal to a is the candidate for local maximum or local minimum. Now how to decide that x equal to a will give us local maximum or local minimum, or how to check whether f of a will be local maximum or local minimum. So for that we have learned a second derivative test. We know that if function is differentiable, then if second derivative at this point is negative, then f of a is local maximum, and if second derivative at point a is positive, then f of a is local minimum. So we are going to generalize this second derivative test for functions of two variables also. So first we will find out critical points of this fxy by solving these two equations, del f by del x equal to 0, del f by del y equal to 0, and suppose the point AB is obtained by solving these two equations. There can be more than one points also. Now we will find out these second order partial derivatives. Fxx, that is del square f by del x square, del square f by del x del y, and del square f by del y square. And we will assume in the second derivative test that all these partial derivatives are continuous, therefore these two are always equal, and we denote these derivatives by these notations. We denote fxx by r, we denote fxy equal to fyx by s, and we denote second order partial derivative with respect to y by t. So we will find out all these second order partial derivatives that we will denote by rst, so that every time we don't have to write these expressions. After this we will obtain value of r and this quantity r into t minus s square, r into t minus s square. So there are three possibilities for this r and rt minus s square. First possibility is r is negative and rt minus s square is positive at point AB. So we will remember, if r is negative, that is second order partial derivative with respect to x, and this quantity rt minus s square is positive at point AB, then in that case f of AB is local maximum. So it is going similar to this one. If second derivative at point A is negative, then f of A is local maximum. Here we are considering this second order derivative with respect to x. So if r is negative and this quantity must be positive, rt minus s square, at point AB, then f of AB is local maximum. Now another possibility is r is positive and we keep rt minus s square positive. If r is positive and rt minus s square is positive at point AB, then f of AB is local minimum. So if second order derivative is negative, we are having local maximum. If second order derivative is negative, we are having local maximum, and if second derivative is positive, we are having local minimum. So same thing here. If second order derivative with respect to x is negative, f of AB is local maximum, and if second order derivative with respect to x is positive, f of AB is local minimum. And in both the cases, this quantity rt minus s square must be positive. For local maximum or local minimum, rt minus s square must be positive at that point. Now suppose rt minus s square is negative, then function is neither maximum nor minimum at this point. F of AB is neither local maximum nor local minimum at point AB, and in that case this point AB is given special name. It is known as saddle point of the function fxy. Saddle point means that point in the domain of given function at which function is neither having local maximum nor local minimum. And the last case is rt minus s square is 0. If rt minus s square is 0, then this test fails. We cannot apply second derivative test to decide local extreme values if rt minus s square is 0. So for that we have to use either definition or some other results. But in our course we will not have rt minus s square equal to 0. So we will not worry about this. We will worry about rt minus s square is positive or negative. If rt minus s square is negative, function is neither maximum nor minimum, and if rt minus s square is positive, function is either maximum or minimum. Now maximum and minimum will be decided with the sign of r. R means fxx or second order derivative with respect to x. If second order derivative with respect to x is negative, f of AB is local maximum. If second order derivative with respect to x is positive, f of AB is local minimum. So we will keep in mind all these things. In upcoming lectures, we will discuss problems on this local maximum and local minimum values. We again recall or summarize this second derivative test for local extreme values. We are going to apply this test for solving problems in upcoming lectures. Suppose that fxy and its first and second partial derivatives are continuous throughout a disk centered at point AB, and that del f by del x and del f by del y at point AB equal to 0. And we have considered this notation. We will remember r is the second order derivative with respect to x, s denotes the mixed partial derivatives, t is the second order partial derivative with respect to y. Then f has a local maximum at point AB if r is negative and rt minus s square is positive at point AB. For local maximum, r must be negative. For local minimum, r must be positive. For local maximum as well as local minimum, for both of these, rt minus s square must be positive. If rt minus s square is positive, then we may have either maximum or minimum. Maximum and minimum will be decided with the sign of r. If r is negative, local maximum. If r is positive, we are having local minimum. And if rt minus s square is negative at that point, then f has neither local maximum nor local minimum at that point. This type of point is known as saddle point of given function. Sometimes they ask the definition of saddle point of a function. So we can write that the point at which function has neither local maximum nor local minimum is called saddle point of a given function. The test is inconclusive at point AB if rt minus s square is equal to 0 at that point AB. So we will remember this second derivative test for local extreme values. We will remember these definitions also. Sometimes they ask the definition of critical point and saddle points. So this is all about this session. In this lecture we have discussed about local maximum and local minimum values for functions of two variables. And in upcoming lectures, we will discuss problems on how to find out local extreme values for functions of two variables. So this is all about this session. I hope you like it. Thank you very much.